Hello, I'm Claire Gilliam, and this is my presentation on Lab 1 on charge tape. First, we have our introduction. So, what is this lab's purpose? Well, we wanted to observe and determine charges on two pieces of tape and compare those observations with our computational models. And the tools we used in this lab were Scotch tape, which we used as our charged objects, and then we used glow script to demonstrate the electric and gravitational forces on the tape. The fundamental physics principles used were Newton's second law, which states that the net force is equal to the change in momentum over change in time, which can be written as the net force is equal to mass times acceleration. Then we also use the gravitational force equation and Coulomb's law to determine the charge on the tape. The results were we found the tape did have an electric charge, and we found the charge, and we also saw that the glow script's models predicted charge was slightly different, however close to our observational charge. Modeling the experiment, we assume that the long tape can be considered a point charge and that each tape has the same amount of charge and is equally distributed. And then when we define the system, we see that we define it as both the top and the bottom tape, and then the surroundings are everything else, so the table or the stands or anything else. The free body diagram shows that as the top tape, or tape B, levitates, its velocity is 0, which means that net force is 0. So this means that the electric force and gravitational force are equal in magnitude but opposite in direction. So next we have our experiment and observations. So running the experiment, our initial conditions were the length of the tape is equal to 0.2 meters, the width is 0.02 meters, and the mass is 2 times 10 to the negative 4th kilograms. And our final condition, or the distance it took to make the tape B levitate, is 4 times 10 to the negative 2 meters. And the tape being attracted looked like this when we stuck our hand next to it, as our hands were positively charged and the tape was negatively charged. So the procedure was to stick and remove the tape from a bottom tape attached to the table to create a charge on both tape A and B. Then we suspended tape B onto two objects to make it float, and then we held tape A up to tape B and measured the maximum distance it could be away from tape B, where tape B would still float. So, calculating the gravitational force, we use mass times G, or 9.81, and we found that the gravitational force is 0.001962 newtons. We set this equal to the electric force since we knew the net force is 0, and then we used this Coulomb's law to solve for Q, which is 1.866 times 10 to the negative 8 coulombs. So, then calculating the electron deficiency, we divided the charge by the charge of an electron to get 1.166 times 10 to the negative 11th. We then found the number of atoms on the tape surface area by dividing the area of the tape by the area of an atom, which we then get as 4 times 10 to the 17th. Then we used both of these numbers to divide the electron deficiency by the number of atoms to get 2.915 times 10 to the negative 7th to get the number of deficient atoms per number of atoms in total. And then, taking the reciprocal, we get there is one deficient atom for every 3.29 times 10 to the 6 atoms. So next we have our computational models. So we were able to plug in our initial conditions and our constants from our observations, and then we created a function that allowed us to input the force of gravity, which we find through the model, into a function that solves for the charge on the tape using Coulomb's law. When we plug in all of our numbers, we get that the computation says that the charge of the tape is 1.86762 times 10 to the negative 8. This is extremely close to our observed value. And so they're not the exact same though, so possible errors could have been that the charge transferred from the tape to our hands, which could have made it more neutral, and that the charge is not equally distributed along the tape like it is in the model where it's a point charge. So we have our discussion and conclusion. So, what if the charges of electrons and protons switch? Well, it wouldn't really matter, because even if both tapes were positively charged, they would still repel since they're two like charges, and like charges repel. So we would experience the same floating effect. And why is it important to handle the charged tapes as little as possible? Well, we just have to ask what happens when the tape came into contact with our hands. The charge from the tape went off into our hands, making the tape more neutral, which therefore made the experiment less effective as both tapes had less charge. Thank you.